Huy give us his second talk, this time about a completely different subject.
Thanks everyone for coming. So, right, about a year ago, before I got to spend my wonderful time as a member in the group, I gave some talks here that is actually along the same theme. So last year I talked about independent sets in dense random Cayley graphs, and more specifically Ramsey Cayley graphs. And you don't have to really remember what happened then for this talk, but just to reiterate, the main punchline there was to understand additive combinatorics and sets with small doubling more specifically from a purely combinatorial viewpoint. And today, we'll kind of wrestle with roughly the same kind of object, so sets with small doubling, but you'll see that instead of a combinatorial viewpoint, we'll take a more probabilistic viewpoint. And I hope that's another interesting development in this story. And so let me start with, again, the key definition throughout this talk. So for us, the Cayley graphs and random Cayley graphs that we work with are defined as follows. So we fix a finite group G. And as usual, given the group G and a symmetric subset of G, you can define the Cayley graph with that generating set. So given a subset S in the group G, and which is symmetric, so in particular, S inverse is equal to S, you can define the Cayley graph with generating set S. This is a graph with vertex set G, and we will put an edge between two group elements X and Y if X times Y inverse is an element of S. And in another abelian group, this symmetry condition we have carefully put down in order to make sure that this definition makes sense, that we are defining an undirected graph. Okay. And there's a very natural random distribution that we can endow on this collection of Cayley graphs in a group. So in particular, given now density parameter P, P0, 1, we can define the random Cayley graph and I'll denote this random Cayley graph by G of P. This will be a random Cayley graph with a, this will be defined by taking a random generating set S, and here we'll take the most natural distribution that we can take, which has a random generating set S, which include or which contain each of these equivalence classes GG inverse independently with probability P. And for this talk, as we will soon see, we're rather different from what we did last year, where we kind of want to have a very general discussion, and we stayed with non-abelian groups throughout much of the discussion. But today, when we go to the sparse regime, which is a lot more challenging, we'll soon restrict ourselves to the setting of abelian groups. And over an abelian group G, there is actually another version of the Cayley graph that will be convenient for us to look at later. And these two notions are closely related. So any technique that we develop for one often translate to say something about the other model as well. So in this case, if G is further assumed to be an abelian group, we can define a Cayley sum graph. So now, given an arbitrary subset S of G, we no longer need any symmetry constraint. We can define the Cayley sum graph with generating set F. Again, this is a graph where the vertex set is identified with the group element. And where now we connect two group elements x and y, even only if the sum x plus y is an element of this generating set S. And as before, for a parameter p in 0, 1, we can define a random Cayley sum graph. For G plus of P. And later on in the talk, when we just focus on Cayley sum graph later, allow me to drop this plus notation when it becomes clear that we will only be restricting ourselves to the Cayley sum graph, but that's a little bit later in the talk. But to define this again as before, we just simply take a generating set S, where each element in the group G is included in this generating set independently with probability P. This is a Cayley sum graph with generating set S, where each element in the group is in S independently with probability P. My apologies for.
How is this different from the other definition? Like something about y becoming minus y?
Right, so in this abelian case, the previous definition, we would include an edge between x and y if x minus y is an element of the generating set S, and in the sum version, which kind of for now only makes sense over an abelian group, we include an edge if x plus y is an element of the generating set. They are closely related, as you can see, at least over abelian groups. And yeah, for most of the analysis, it doesn't quite matter which one we're talking about, at least in what we will be discussing. But there will be some small differences. The a minus a and a plus a behave differently in some cases. There may be a factor of 2 that's flying around because addition is symmetric, but the subtraction is not. But these are small differences. Okay.
Are you including the identity element with probability P in S, or are you?
Yeah, so let's think that the identity element we will always ignore. And I want to consider undirected graph with no loops. So let's keep the discussion simple that way. Okay, so the main question that we will try to investigate in this talk is this is one of the parameters that you can look at for random Cayley graph. Of course, there are lots of parameters that you can look at, but this is our focus. What is the independence number? So the size of the maximum independent set in this random Cayley graph GP, or in the random Cayley sum graph G plus B. So let me start with maybe one of the good way to produce a general bound on the independence number in a random Cayley graph or Cayley sum graph. And this follows from observing that for the random Cayley graph model, it is actually very easy to control its spectral expansion. So we can bound the non-trivial eigenvalues of a random Cayley graph or Cayley sum graph actually even in an easier way than what we can do for a random graph or a random regular graph. So let me just take it here without regressing that by a result of Allon and Rochman with high probability, we have that all of the non-trivial eigenvalues of the adjacency matrix of the non-trivial eigenvalues of G of P is of order at most big O of, well, the typical random Cayley graph GP will be a regular graph with degree very close to n times P. And so the optimal eigenvalue, the optimal bound that we can put for the non-trivial eigenvalue will be square root NP. And the reality is not much different from that. So up to small log factor, all of the non-trivial eigenvalues will be bounded by square root NP times log n. So square root D log n, where D is the degree of the random Cayley graph. And in particular, by Hoffman's bound, we can immediately put an upper bound on the independence number of GP. So alpha of GP is going to be at most big O of square root n log n of P with high probability. And of course, this is even if P is a constant, we see that this upper bound is stuck at order around square root n, which is kind of what we expect if we only access the independence number via a spectral quantity. Okay, so of course, we expect that the independence number of a random Cayley graph GP will be significantly smaller than this bound. But I'll get to it later. We expect that maybe the independence number of the random Cayley graph GP it behaves roughly the same as the independence number of a random regular graph of degree p times n. And in which case, we expect to have a bound here that is significantly smaller than square root n over p. So I said this is in the dense case where p is a constant. This is pretty much the focus of what I mentioned last year. So maybe I just, for context, reiterate some of the knowledge that we have in a dense case before we go into the sparse case. Okay, so in the dense regime, and in particular, I mean, we are fixing P as a constant as the size of the group G grows. And actually in the dense case, let's just focus on kind of the most sensible case, which is when P is equal to 1/2. And obviously in this case, the distribution of the independent sets and the cliques in the random Cayley graph is perfectly symmetric. So what you prove about the independent sets also apply to the cliques. And then we have applications in Ramsey theory. That's why we had lots of discussion around Ramsey Cayley graphs when we discussed the study of the independent sets in a dense regime. And roughly the best bound that we know in a dense regime where P is a constant is a big improvement over this bound of square root n over P, or square root n in this case. This is a result in joint work with David Kummer, Jacob Fox, and Liana Yepremian, where we show that for every group G, so for this one, we don't need the abelian condition, the independence number of G of 1/2 is of order at most big of log G, log G with high probability. And in general, without further assumptions on the group, this bound is tight. So you remark?
The Boolean cube.
Yeah, this bound is tight for, well, the Boolean cubes, but actually any group that looks similar to that. So any group of the form Fp, let's not use, let's Fq to the D for, let's say, a constant prime power q as D grows. And let me still mention that given this result, the only more precise bound that we know now comes from a theorem of Green earlier, and then was sharpened by Ben Green and Rob Morris, where they show that for the arguably nicest abelian group, Z mod n for prime n, we can actually obtain a much better understanding of the behavior of G1/2, which is significantly different from these finite few vector spaces. So they can show that the independence number is actually asymptotically the same as the independence number in an Additive random graph, Gn1/2, which is about 2 times log base 2 of n. Okay. And we'll later in the talk, we'll revisit this result later, and hopefully then I explain to you a little bit more why this behavior holds true in this nice abelian group, but not in other abelian groups. Okay. So
Sorry, you don't need like n to be a prime or anything for that?
yeah, so for this one, we don't really need the n to be a prime. I think when in their paper, they did restrict themselves to the case when n is prime. Maybe that's just a sensible case to consider, but we expect that for this type of behavior, we don't rely so much on n being exactly a prime. Okay. Okay, so before I go further, particular to the
Roughly speaking, the difference in behavior is because of the number of subgroups.
yes, exactly. So this is something that we mentioned last time. So what is significantly different between this type of group and other abelian groups, even more generally cyclic groups where n is not necessarily prime, is that these groups contain way fewer subgroups than these ones. And in fact, we can get a fairly precise characterization. So If we get some bound that is large, let's say asymptotically bigger than log G, then that must be caused by the existence of many subgroups of a small size inside a group G. No, go much further into that direction. So I just briefly mentioned here how we approach these type of results. And well, if you remember what happens in an Additive random graph, so if you look at Gn1/2, how we control the independence number of Gn1/2 is simply just to write down the first moment or the expected number of independent sets of a specific size in the Additive random graph Gn1/2, and it will be an easy calculation to check that for the appropriate parameters, that first moment is very small, so that is a first moment obstruction to existence of a large independent set in the Additive random graph Gn1/2. Let's try to just repeat that same story, but now for our different ensemble of random Cayley graph. So the first moment, which is the expected number of independent sets, of size T for some appropriate parameter T that we will choose later inside the random Cayley graph GP. And of course, a similar formula applies to the Cayley sum graph G plus P. This can obviously expand out in the following form. This is a sum over all subsets of the group G of size equals to T. And here we would need to compute what is the probability that this subset A becomes an independent set in this random Cayley graph GP. And it's not hard to see that that probability is roughly 1 minus P raised to a power that is of order A times A inverse. So here, because of the symmetry constraint that we put on a generating set, there may be a factor of 2 that is lurking here, but let's ignore this constant factor. The main point is that this probability is dictated by the size of this product set A times A inverse. So here, as always, A inverse is the collection of all elements of the form A times B inverse, where you draw A and B from the set A. So in an abelian group, this would become A minus A. If you are looking at the Cayley sum graph over an abelian group, what you would put here is the size of A plus A instead of A times A inverse, but we'll see it exactly kind of, we can see what goes into that exponent. So obviously, the big terms that are problematic to us are exactly the terms where the set A has size T, but the product set A times A inverse has too small size, which would cause this probability to be too big. So let me just say that in order to prove, for instance, this result, all that you need is the following counting bound that would give you control, sufficiently good control on the first moment. So this result, we show that for all group G, the number of subsets A in G of size T and the product set A times A inverse is small, at most K times T. So let me note that there's no constraint that I'm putting on this parameter K. It's an arbitrary parameter that ranges between 1 and T. And the number of these sets, we get the following sharp bound up to absolute constant is at most the size of the group raised to the power and some absolute constant times K plus log T. And then we have some other constant times K raised to the power T. And in general, this counting bound is sharp. So all of the terms there are needed. It is optimal up to the constants hidden in the big O. Okay, so this is kind of a reminder really of the story that I discussed last year. And I will not go into much further detail here, but there's one lesson from that talk that will become important to us when we go to the sparse case, even if we restrict ourselves to abelian groups. We may see this only in today's talk, but the main point of the proof of this result in our paper is that we really prove this by forgetting about a group G, and we move to a significantly more general combinatorial model of the Cayley graphs, and in particular, what we prove, in fact, holds in this general combinatorial setting. Where we are only given some proper edge coloring on, let's say, a complete graph. And we want to count the number of vertex subsets inducing few colors in this edge coloring. And we can quite easily see that this is a generalization of this group theoretic setting. So given any group G, we can consider the complete graph where the vertex set is identified with the elements in the group G, and between two elements X and Y in the group, the edge XY, we put the color, which is just the label corresponding to the product X times Y inverse. And this is not exactly a proper edge coloring, but it's very close to being a proper edge coloring. The maximum degree of every color class is going to be at most 2. So in fact, it's quite easily, I'm not doing this all precisely here, just kind of a brief punchline of what happened last time. The main point is that we can just think about the information given to us by the group in terms of this proper edge coloring that we endow on the complete graph, and then everything that we want to obtain in the group theoretic setting, including results like counting sets with small product sets, we can do all of them already in the combinatorial setup. And this has a few interesting corollaries, even if you only care about abelian groups. So we use it, for instance, to prove one of the conjectures of Ruzsa's around the structure of sets with small doublings in abelian group with bounded exponent. And this is, again, exactly the angle that will be helpful to us later. When I now turn to the discussion of sparse random Cayley graph later on in the proof, we will need some robust versions of results in additive combinatorics that are otherwise quite hard to obtain. But given the combinatorial perspective that we have from this dense random Cayley graph project, we get quite a lot of advantage in analyzing, improving the additive combinatorial results that we will need when we analyze sparse random Cayley graph. Okay, so kind of a very quick summary of the dense case, but is there any question on that end? Not. Let's go to the interesting case now, which is a sparse regime. So in this sparse regime, we are thinking about the density of the random Cayley graph as some parameter that goes to 0 as the size of the group goes to infinity. And the main challenge in this case, which we can already observe if we take the group G to be any nice group, let's say a nice abelian group like Zn, is that there's no chance for this first moment, as we wrote down here, to be small. Okay, so in fact, for any parameter P that tends to 0 as n tends to infinity, the first moment is always too large. And the reason is as follows. The number of sets A, size T in Zn with small doubling. So let's say with, now I'm in an abelian group, so allow me to write here instead of AA inverse, A minus A, with very small different set, so at most some absolute constant times the size of A, this is always at least some exponential in T. And it's easy to see this. For instance, let's say this is some constant like 5. You can, in Zn, you can start with any small interval, let's say of length 5 times T, maybe some slightly smaller constant times T, but still much bigger than T. And let me put here 10. If you take any subset A of this short interval, the different set will be contained in an interval that's at most twice the length of the interval that you started. And the number of sets of size T inside this interval that have size, let's say 2T, will be very large, will be at least exponential in T up to an appropriate constant. And if you plug this in to this probability over here, we get that the contribution from these sets to the first moment is at least around, well, minus P times 10T times an exponential in T. And this is always very large. And this is the contribution to the first moment. as we wrote down over here. So clearly, the first moment will not, at least the naive first moment that we wrote down, will not allow us to rule out the existence of large independent sets in a random Cayley graph as long as it becomes sparse, no matter how fast speed tends to 0. Well, but this is maybe the small part that links us today to the talk last week. We know already from last week that the first moment still should allow us to explain everything that we need. And so in this case, the naive first moment fails to tell us the phenomenon that we expect. But in particular, that means that there must be a way for us to construct a more efficient cover in the language of the talk last week for this collection of sets that we care about, the collection of sets of the form A minus A. And that's exactly the route that we will take now in analyzing this sparse regime. Okay. So maybe lesson from last time. We must be able to find a more efficient cover for this collection of sets, A minus A. Well, in a non-abelian group, it's abelian for the example, but in general, we care about the collection of the sets of the form A times A inverse, where A is a subset of G and A have an appropriate size T.
This is a formal moral of the story last week or an intuitive moral?
This is a formal.
Formal, because that's again the optimum of some selection process.
Yeah. And you can think about this as in terms of the results around thresholds, so the Cayley conjecture tells us that, yeah, if we don't expect the large independent sets to appear, at least up to some small modification, we had better have an efficient cover for this collection of sets. These sets play the role of the hypergraph, the target structure hypergraph that I mentioned last week. And really in exact parallel to that, what we want to find is a cover for this collection. And to recall, a cover for this collection of sets means some other collection of subsets of the group G for which every set of the form A times A inverse contains at least one set from that collection. Okay, and we want to construct such a collection in which this type of union bound proxy now gets to be very small instead of this one, which is abnormally big. Okay, so let me start with maybe the following result, which has a very neat proof. So this is a theorem of Noga, goes back to 2007, and kind of more officially appears in a later paper of his. So in this case, he shows that the independence number of a random Cayley graph, GP, this is at most order big O of p to the minus 2 times log G squared with high probability with. Okay, so this is a bound that is better than the spectral bound of square root n over p whenever the parameter p is not going to 0 too fast. So even if p goes down polynomially in the size of the group G, if it doesn't go down too fast polynomially, then this would give a significantly better bound than the bound of square root n over p from the spectral bound. And in fact, of course, we can ask, well, what happens if p is a constant, just to relate this general bound to the dense story that we discussed before. When p is a constant, this gives a bound of log G squared, which was exactly the best upper bound for dense random Cayley graph in general group that we know prior to our work. And just to connect the two stories in a coherent way, we can actually use our argument or use our counting result still, combined with an additional argument that I will tell you now, to show that in general, we have the following upper bound on the independence number that smoothly interpolates between the sparse and the dense regime. So we get a bound of the form, the bound will be a bit clumsy. So we'll have two terms. The first term is p to the minus 2 log G and roughly log 1 over p. And the second term is p to the minus 1 log g log g over log p inverse. It's just kind of what the argument gives. And the main point is if you plug in p, which is a constant, then in this bound, we will actually see that the first term would just have order log g, which is wonderful, but it's not always true. And the second term will give us exactly this term log g, log g that we have in the dense case. And when we go to the sparse case, then it kind of, this always behaves better than the bound that we stated here of order p to the minus 2 times log the size of the group squared. Okay, so I want to tell you roughly how we can prove this. This is the first and simplest version of the cover that we will construct for this collection of sets, and we will progressively move to more complicated covers. So given a subset A in the group G with A times A inverse at both K times T and A of size T always, we can consider the following two cases. So in case 1, the doubling, if the doubling K was already large enough, then we can just directly apply this counting bound, and we'll be able to see that if the doubling K is large, if A times A inverse is sufficiently large, then combining this counting bound with this probability still give us a very small term. So the contribution of these terms to the first moment is still small, and we can just go with counting instead of having to switch to a smarter cover. So in this case, if K is bigger than order P inverse, roughly, then we can just apply directly the counting result. So we honestly count all of the sets A with that doubling. Let me write here, equal to KT, to avoid some generosity in this discussion. And in the second case, we need to handle all of the sets with doubling K that is too small differently. So if K is smaller than some constant times P inverse log P inverse, then we will do the following. And this is the first cover that we will construct. Move to this board. Okay, so what do we do with the sets with small doubling? So we show that any such set A, okay, with doubling K that is smaller than roughly order P inverse, any such A contains a subset A prime with the following two property. The size of A prime is now significantly smaller than the size of A. The size of A prime is smaller than square root of KT. So when K is small, this is much smaller than T, which is the size of A. And furthermore, the product set A prime times A prime inverse is still very big. Actually, it's still a constant fraction of the product set A times A inverse. Okay, and to prove this, the proof of this is actually very simple. How can we find a subset A prime? We can just take a random subset A prime of A of size A prime, let's say equal to square root K times T. And you can check that the expected number of elements of A times A inverse that will land inside this product A prime times A prime inverse. This is always at least some constant times the size of A inverse. Let's say a constant times K times T. So there always exists a choice of a subset A prime with the property that we require over here. We can just take an appropriate random subset of A. And now what is the cover that we will construct for the collection of sets A times A inverse. In this case, we will put just all of the sets A prime inverse that arise this way into the cover for this collection of sets A inverse. And in this case, we are restricting ourselves to sets of size T and doubling, let's say, K times T, and K is smaller than some constant T inverse log P inverse.
A quick way to see why this is important for the random argument to.
So why the
I
random?
mean, why roughly P inverse is enough to.
Yeah, we'll see this now. Yeah, why P inverse is enough for this value. So what we will need to check, right, is that this cover, well, we can see immediately that it is a cover, right? For every set A in this collection, there exists such a subset A prime of A, and we already put A prime times A prime inverse into our cover, then this is clearly a subset of A times A inverse. So everything in this collection over there is perfectly covered. But what we need to check now is that the cost of this cover, the union bound proxy that we can calculate from this cover, is not too big. Okay, so let's compute that.
No, but I was asking about the fact that A prime times A prime inverse is at least.
Yeah, so my point is that for this
The
one,
value of P.
so for this one, we actually don't need to use yet our assumption on K.
You don't have, this is true for every case.
Yeah, this is true for every K.
Right?
Yeah, this one is true for every K. We'll only use the assumption that K is more now.
Yeah. Okay.
Yeah, so when we come,
So the cover, which A primes are you putting all of
yeah,
them?
so for every set A with this property,
You choose one of them.
there's one of the A prime with this property. You choose an arbitrary choice you want with these properties, and then we put the corresponding set A prime inverse into our cover. Okay, so the cost of the cover is now roughly the sum over these sets A prime. Well, any such A prime has a small size, right? So it is at most the sum over A prime of size square root times T, with the further property that A prime inverse is large. Let's say bigger than some constant times K times T. And inside here, we have exactly the same term that we had before. So 1 minus P, and now we put in the exponent A prime times A prime inverse. Okay, okay so far. Right? So now let's bound this term. This is roughly smaller than exponential this is roughly exponential in minus P. P is small. And here we have a lower bound of order some constant times K times T. On the other hand, what's the number of terms that we have? What we gain now from passing to A prime from the set A is that the number of terms in this summation is significantly smaller. Right? The number of terms that we have is at most n to square root kt, where n is the size of the group. And now we can see that this is roughly exponential minus pkt plus, let's say, square root kt log n. Okay, and under the condition that, yeah, right. You can check that under this condition on K, and if you take the parameter T to be what we claim in this theorem, don't order the exact detail, maybe you can just take the parameter T to be this bound over here, then we can check that that quantity that we computed over there is going to be very small. Okay, so. Yeah, so in fact, if you care about this bound, you don't have to split into the two cases at all. The split into the two cases was kind of to get this kind of more messy bound, but interpolates correctly to the dense regime. Okay. Maybe I can do quickly this check. So to see this, we can check what we need in order for this term to be small. And in order for this term to be small, this is true when, well, we have that t times k times t is much bigger than square root kt. Let's say square root kt again, if you wish. And here, this is true in particular when t is much bigger than, well, p to the minus 2 log n squared. And actually, there's a 1 over k here. But in particular, k is always at least 1. So when t is larger than p to the minus 2 log n squared, we will always have that this type of term is very small. Okay. Question about that sketch of the proof? Yes.
Can you explain again why the expectation of A prime versus like omega kt?
Yeah, sure. So for that point, one, let's try to compute the expectation of A prime inverse. Okay, so yeah, so let me say this. Jumping ahead of myself a little bit.
It's a graph theory, thing, right?
Yeah, this is
You are looking at, I mean, you have a dense graph, and you are
right.
looking at a sparse set that spans most of the edges.
Right. So Peter, you do have to be a little bit careful here. If you assume that you are working in the setting where A has doubling K and every element in the product set A times A inverse is represented roughly the correct number of times, then you can do this expectation calculation correctly and it will give you a constant times KT. In general, it's not always true that each element in the product set is represented a correct number of times. You can always still go to the correct dyadic level in which the elements are represented the correct number of times. We will see this argument more precisely in a little bit when I discuss the more sophisticated cover. So here, one do have to be a little bit careful and maybe just for me to simplify this discussion right now, before having to do that dyadic partition, let us observe that in this case, if you are anyway in the end only going to target this type of bound, let's not go into the messy bound that I stated over there right now. You can actually just forget about K in this entire discussion, right? So as long as you can find a subset A prime of phi square root T with this property on the doubling, then everything still goes through perfectly here. You lose this factor, but you never gain from it anyway. And this is actually much easier to prove. You don't have to pass through this dyadic partition. And now this is some kind of direct calculation that we can check, but maybe I don't check it right now. Okay, that fine? Yeah. So from now on, our goal is to try to improve on the exponent that we currently have from this very simple cover that we constructed. So the simple cover gives us an exponent that is roughly p to the minus 2. And also from now on, when I go to the sparse and more sparse regime, I will just forget about the factors that is just log in the size of the group. And that will keep at least the discussion a little bit simpler to follow.
We should think of P as some polynomial.
Yeah. So if you wish, for now, think about P as some polynomial in n to the minus c for some small constant c.
And you want to replace exponent 2 with exponent 1.
Well, yes, ideally we want to replace it with an exponent 1
Up to logarithmic.
up to logarithmic factor. But for now, we are content with some improvement on that exponent. Yeah. So, okay. As Avi just mentioned, what is the guess that we should have on the independence number here? Conjecture, proposed explicitly by Noga, that the independence number of this random Cayley graph GP should be perhaps at most up to log factors in n order P inverse. And this guess would be sensible if you believe that a random Cayley graph of density P behaves roughly in the same way as a random regular graph with degree P times n. Okay, so before moving further into the bounds that we know for the independence number, let me mention an interesting connection to a problem in additive combinatorics. And that was actually one of the first motivation for Noga to look at the independence number of a polynomial sparse random Cayley graph. So there's this question, was Ben Green, and Green and Gowers had some very early works around it. So he asked, what is the minimum size of a subset T inside, let's say, the cyclic group Zn, where n is a prime, such that the complement Zn minus T cannot be written as a subset B plus B. For any subset B of the cyclic group. Okay, so as we will soon see, every set in Zn that is sufficiently large, let's say very, very close to n, we can always write such a set as a subset B plus B. But at some point, as the size of that set gets smaller, gets further and further away from n, we'll be able to find sets that cannot be represented as a subset. The question is, where does this transition take place? And Noga showed in particular that the minimum size of such a set T is always between to a lower bound, which is n minus order n to the 2 roughly, and the upper bound, which is roughly n minus order root n. Okay, so this in particular means that every subset of Zn. Okay.
Yeah.
I mean this. Sorry, I forgot that I just switched to complement. This means that every subset that is almost all of Zn, apart from around root n elements, you can always write them in terms of a subset B plus B. And there exists a subset of Zn that misses around n to the 2/3 many elements that cannot be written as a subset B plus B.
Can I ask you a question in terms of the independence set?
Yeah, I will.
I mean, the bounds follow from the bounds on the independence.
Yeah, so
you can really.
it maybe to state it, we'll see that it's closely related. I don't know the cleanest way to state directly this in terms of the independence. But yeah, okay, there should be such a way. But anyway, I will tell you now how this is related to the independence number of the random Cayley graph. So
You flip the O and.
yes, sorry. I flipped the O and omega, thank you. Okay, so how is this related to what we have so far? There's this alone made a conjecture here that the minimum size of such T is of order theta tilde n to the 1. Okay, and now I will explain to you how this conjecture is a corollary of this conjecture. Okay, so what is the connection? And in fact, in general, we can prove that if you can show that the independence number of the random Cayley graph GP is at most order p to the minus a for some parameter a with high probability, then you can obtain that the mean size of t such that Zn minus t is not a subset. This is going to be at most p to the precise relation n to the a over a. Okay. So to see this, let's take the set T over there for which we want the complement of T not to be a subset B plus B to be written in this way. So let's take T to be the union of two sets, T1 and T2. Let's not talk about T2 yet, but we will in the end choose both T1 and T2 to be of roughly the same size, and they will have size be about P times N, where P is an appropriate parameter that is of order n to the minus 1 over a plus 1, where a is the bound that we have here. Okay, so we will choose the first piece T1 just randomly. So just choose first T1 randomly. So we observe that if T complement is equal to a subset B plus B, then this is actually just the same. Sorry, if T complement is equal to B plus B, then B plus B intersected with T1 is empty. And this is exactly the same condition as saying that B is an independent set in the Cayley graph with generating set T1. So by the bound that we have on the independence number, with high probability, we need to have that the size of this set B is not so big. It's at most order big O tilde of P to the minus A, which you can make sure that this is much smaller by some, let's say, polylog factor compared to the size of T, which is P times N. Okay, so we just chose the parameter P in order to guarantee this condition. Now, in particular, if every single set T of this form T1 union T2 can be written as a subset B plus B, now we have fixed the piece T1. So now B can only range among all of the sets that have size much less than P times N. And yet we have many ways to choose the set T2, which is a subset of size P times N. This means that the collection of B's that we can use is smaller than the collection of T2s that we can choose. And in particular, there have to exist a T2 for which no B satisfy that the complement of T is equal to B plus B. Okay, so there exists T2 such that for T equals to the union of T1 and T2, T complement is not B plus B. For any B smaller than P times N, but then also in particular for any subset B of N. Okay, so this is the connection. We see that if we have an exponent of P to the minus 1, then we'll get the bound of N to the 1/2 for this question of Ben-Green. And in general, if we have some other exponent, then we get some improvement over the exponent of N to the 2/3 in Nodel's result. So right, with that, let's get to the first results in the sparse case that we will discuss. So first result that I will tell you about is a polynomial improvement over the bound of p to the minus 2, roughly, up to log factors of Noga earlier that we discussed the proof of. So in general, we have that the independence number of GP, second, now we are going to focus on abelian groups. Or abelian groups G. The independence number of GP is of order at most p to the minus 3/2 with high probability. So halfway between the conjectured bound of p to the minus 1 and the previous bound of p to the minus 2. And this also holds true for the Cayley sum graph. And we'll get back to the Cayley sum graph a bit later on in this talk. So in particular, as a corollary, we obtain that the minimum size of a complement T such that n minus T is not a subset. This is bounded above by order n to the 3/5. Okay. So what I will do now is to discuss the ideas behind the proof of this result. And after that, if we have time, I'll get to the discussion of what happens in more specific abelian groups, let's say Z mod NZ, where if P is a constant, like 1/2, we actually know that the independence number is asymptotically the same as the addition random graph. So that's a much sharper behavior. And we'll see if we can, how we can push that sharp understanding to a sparser regime. Okay.
If you want to take a break, or maybe the audience needs to.
Yes, yeah, let's take a 5-minute break. Okay, super. I shall resume. So before going into the main part, I'll just quickly remark that with the way that we built the cover earlier, the sketch of a simple cover that we constructed earlier, we cannot improve over the exponent of p to the minus 2. So let's maybe just quickly convince ourselves that given all of the best that can happen to us, we can't really improve on that bound. So maybe let's start with a set A for which the product set is of the same order as the size of A. This will be roughly the worst case, as we will see. And maybe you now wish to stay within an abelian group. You can also take this to be just A minus A. Now, if you want to build a cover that comes from a subset of A prime, and the cover consists of a set that looks like A prime minus A prime, well, in order to get this set to have, well, what do we need? We need P times the size of A prime minus A prime. This is the tail that we have in the probability to be much bigger than, let's say, the number of choices for the set A prime, which is the size of A prime. This is going to be at most P times the size of A up to a constant, because the doubling A minus A itself is just of order A. And furthermore, in order to get such a bound, we will need A prime to have size at least bigger than square root times the size of A. So in order for A prime minus A prime to capture something like A many elements, we will need it to have size at least square root A. And if we chain together all of this bound, we are forced to consider set A for which its size is roughly bigger than P to the minus 2. So we have to do something differently in order to get a better bound. And let me now write down what is that thing. So the main, we call it the cover lemma, is the following. So here, we will show that there exists a much more efficient cover than the one that we constructed before. In what sense? There exists collections F, actually multiple collections, one for each parameter delta. What are the deltas? So for all dyadic, so delta will be of the form 2 to the minus w for an integer w. And delta will range between something like 1 over k, maybe up to polylog k factors. And think about k as a doubling as always, up to 1. Such that we have the following conditions. So the first condition is the cover condition. For every A in our group G, such that let's say the difference set A minus A, we're focusing on the abelian case now. The difference set, or in fact, maybe just for simplicity of what we will discuss later, let's think about the Cayley sum graph in an abelian group from this point, guarantee that everything that we say will apply equally well to the Cayley graph. And in the Cayley sum graph, the size of, for every set A such that A minus A is less than kt, where the size of A is t. There exists a delta, a dyadic delta in this range. And some set from this cover F delta such that A plus A contain the set F delta. So this is just the usual cover condition. We just need to be kind of a little bit more refined. So these levels delta give us a little bit more refinement in this cover. The second condition is that every set in this collection F delta is large. The size of F delta is at least delta inverse times t, which is the best that you could hope for. To some log factor, maybe no log factors here. Okay, delta times t times 1 over polylog k.
You wouldn't need the row bound. Before you wanted elements in the cover to be small. There be fewer of them and you are doing it.
This is now different. So before, what did we want? We want the size of so before the cover consists of these sets. So we want there to be few of them. That's why I want the size of A prime to be small. But I want the size of this product set to be large. So now the cover that I'm constructed no longer comes with this form even.
Okay.
So we'll see that we'll guarantee that there are few sets in a different way, but each set we still want to be large. Yeah. So every set from this cover should be large. And the last condition, of course, what Avi mentioned, we want the number of sets in the cover to be small. So the total number of sets in this cover F delta is at most, well, we'll have the following bound, exponential. The first bound, which is the more important one, will be order big O tilde delta to the minus 2. So at most, actually k squared, roughly, up to log factors. And the second bound, so this is a minimum, is the one with the more familiar form, which is square root delta inverse t. Okay.
Can this be seen some way as a special case container with in which you have extra properties or
Yeah, so of course this can be think of as
yeah, I mean by definition it can be so, but I'm just wondering if in the general method of containers whether this has added value to some more general set.
yeah, well, okay, so we'll see that counting sets with small doubling in general, which is kind of along the line of what we are doing here, is closely related to container type ideas. So we want to use container to bundle together sets with small doubling to say that they have additional structure. This type of bound is a lot more similar to kind of procedures that you would use typically to build a container. This one is just completely different, as we will see, where we use more additive combinatorics to derive this bound. Yeah, I mean, this argument is quite specially constructed within this world of additive combinatorics. So maybe it's useful for other type of container question within additive combinatorics. But in general, I don't know. Want to remark that the focus here should be on this first term for delta to the -2. So in particular, if k is a constant, so let's think that you are trying to build containers. So this is containers from the inside. So that's why I call it cover. It's kind of in the opposite direction of a usual container. But if you want to build these collections that sit inside the sum set A plus A for sets with constant doubling, so when k is constant, the collection of containers or the collection of sets F delta that we built here will have size that depends only on the doubling k, which is now a constant up to log factors. So it has absolutely no dependence on the size of the set T. And this is kind of the reason why this regime is interesting, that behavior is quite interesting. And of course, you can think that is along the line of structural results in additive combinatorics, right? Like Feynman theorem or Feynman-Ruzsa theorem that would tell us that the sets with very small doubling, they are extremely structured. So of course, we can build a lot more efficient cover for these type of sets, but quantitatively, these results will be very weak to produce any bound that will be usable to us. But this is kind of the counting analog of these structure results. So let me mention that there's a question, think of Shakalovet, that even restricted to the case where, let's say, the abelian group G is a Boolean cube, F2 to the D. And we ask if there is a collection F of subsets of F2 to the D of few sets. So let's say of exponential in D many sets, such that for every subset A of F2 to the D of very large size, so for which the size of A is at least some absolute constant times 2 to the D. Obviously, such a set A must have constant doubling. And he asked whether we can build such a small collection of sets F so that for every A that is large, there exists F from the collection such that F sits inside the sum set A plus A. And furthermore, the size of F is large for every F from the collection. Okay, and you can see that this statement in the regime where we just focus on this first bound delta to the -2 give a complete answer to this question. So even in the case, but that makes the point why it's interesting is that even in the case where you only consider dense sets, huge sets A inside a group, building such a collection of sets F is non-trivial. Okay. So this cover lemma positively answers this question. And so we'll see that the critical case that we understand much less is when the doubling K is very small. Okay, so there's any question about the statement? Otherwise, I will now tell you about the ingredients that go into the. So there are two bounds in the proof, one that is less interesting and one that's more interesting. And I'll tell you maybe first the less interesting one. so that we have all of the pieces together. Oh, actually, maybe before that. So this key lemma, this main lemma, would imply that the independence number is at most p to the minus 3.5, and this is kind of an easy calculation. You can check that once we use these covers, these collections F delta for our covers, then we need to check that the cost of these covers is small, and roughly what goes into the cost of the cover is something like minus delta in p times delta inverse t up to some log factor multiplied by the number of sets in the collection F delta, which is big O tilde delta to the minus 2 minimum with big O tilde square root delta inverse t. And if you take t to be p to the minus 3.5, maybe I'll skip the somewhat boring calculation. We can check that this is very small. So these cover indeed witness the upper bound of p to the minus 3.5 on the independence number.
The exponent minus 2 is what gives you the 3.5, so any polynomial bound.
No, yeah, so any polynomial bound that you can put here would give you some improvement over the exponent of 2.
Yeah.
Yeah, and 3.5 comes from balancing these two terms.
You know, you can't do better than -2 here, or?
Yeah, of course, you would conjecture that here you can put delta to the minus 1, which would give you everything that you expect to be true. Yeah, there are lots of, once you are thinking about additive combinatorics in this regime, there are lots of interesting questions that you can pose that are beyond your usual structural questions that you see. So for instance, if you allow yourself, so we expect that the optimal answer here is delta to the minus 1, that cannot be improved. But if you relax a little bit this lower bound constraint on the sets in our collection, we still want them to be large, but maybe they can be a little bit smaller than delta to the minus 1 times t, then we actually may have significant improvement over even this exponent of delta to the minus 1. But okay, that's maybe a long story that we can discuss later. So now I will tell you some ideas for this main cover lemma. And let's start first with this easier bound. So first, let's try to build such a collection F delta so that the size of F delta is at most big O tilde square root delta to the minus 1 t. And this is closely related to the one that we discussed before, and I'll just use this to kind of set up the tools that we will use in a simpler setting. So first, for some notation. Given a set A in our group G, let me denote this convolution A star A. This will be another function on the group G, and A is the convolution, and X is defined to be the average over group elements Y of AY, AX minus Y. So you can see that if, okay, this A is now the indicator function of the set A, and you can see that, of course, the sum set A plus A is exactly just the support of the convolution A star A. You can let me denote also the density of the set A by this constant little a. So this is the size of A over the size of the group N. So always now N is the size of our group. And in fact, it's no loss in just thinking about the group G as the cyclic group Z mod N. And we'll assume that the doubling is K. So A plus A is equal to K. Yes, we call T the size of the set A. So now let me define the following quantities. Let me define the level set L delta of A. This is the high level set of the convolution A star A. So in particular, L delta A will consist of all elements X for which the convolution A star A of X is at least delta times the parameter A. And you can check that this normalization is the sensible one by checking that you always trivially have the bound that is A star A of X for any element X is always at most little a. Just part of the normalization that we are looking at here. And okay. So now let's start to construct our collection F. So in fact, our construction of F will come with some nice property that we will use later for a different set of results. So the construction of F guarantees the following. For every A with doubling K, in both cases of the construction actually, there will be some set from our collection F such that this set F contains the large level set of the set A for some appropriate delta. Okay, so careful here, this is for some delta, some dyadic delta in the range that we specified before. And we will see later that we'll just choose the right value for delta so that this containment immediately forces a lower bound on the size of F delta. Okay, so now let's do the easy direction of the construction of this cover. So by dyadic, just by looking at it dyadically, by dyadic partition, maybe, there will always exist dyadic delta that is between 1 over k polylog k. We can actually just safely ignore most of these polylogs throughout the discussion now. There exists such a delta for which the level set L delta of our set A is large, and the correct value for large here is exactly about delta to the -1 times the size of A, and here we may have again some log factor. Can ignore this. So now we can sample a random A prime in A that is of size exactly about delta to the -1/2 times A to the 1/2. And here, let me use an additional log factor. Okay, so since every element in this high level set L delta of A has many different representations in terms of A plus B, where A and B are elements of the set A, we can check just by the union bound that not only is the size of A prime plus A prime large in expected value, in fact, because here we pay for a log factor with high probability, the sum set A prime plus A prime will contain this entire level set L delta of A. So in this case, our collection F delta will consist of exactly all of these sets A prime plus A prime. Okay, so the upper bound on the size of F delta, of course, will just follow since the size of A prime is small. And furthermore, it has all of the other properties that we claim.
It's just like before, only that you are doing a more refined calculation according to the
Exactly.
degrees. or
Right.
to the number of representations.
Yeah, so
Each
it tra-
element has in the subset.
that's right. It's exactly as before. Just to address Peter's question before, this is the more precise version then.
So again, it's an argument about bipartite graphs. It's not,
Right, that's right.
there's no group.
Exactly. The group will come for the interesting bound, not this one. Okay. Okay, so if that is okay, I will move now to the other case. Fine. So in the second case, we want to produce a cover F delta with similar properties, but now we want our collection F delta to be bounded above by this other bound.
The upper bound of F delta is exponential in what is the sum of these two?
Oh, it's a minimum of these
The
two.
minimum.
Yeah, yeah. So again, let me reuse the input that we have. So let's fix this dyadic level delta. Delta is somewhat large, at least around 1 over k, and the level set L delta of A is large. Up to log factor delta inverse times the sign of A. Okay. Now this is my construction of the family F. In this case, the family F will actually have the following property. So let me maybe represent the convolution A star A like this. We will have two levels at play. There will be some level delta, and there will be maybe this delta over 2, and there will be the level delta that we have here. And our constructed set F will satisfy the property that for this F delta that we put into this cover, it will be sandwiched between the level set delta over 2 and the level set delta. Okay, so our set F it have to contain all of these elements that is in the level set above delta. And it further fits inside the delta over 2 level set. So how do we find such a set F? This is where we significantly use some information from the group. In particular, we will pass to the Fourier domain. We'll use a Fourier transform. Let's remember that in Fourier analysis, the convolution looks very nice after we pass to the Fourier space. So in particular, the convolution of A star A at X is equal to the sum over all characters chi of the group. And we have here A hat chi squared times chi of X. Okay. And of course, by Parseval, we know that the sum of A hat chi squared in absolute value is exactly equal to the density of A in the normalization that I've chosen. So now this is our argument for finding this set F delta. So we will sample independently and identically distributed characters chi1, chi2, up to chi m for an appropriate choice of m that we will choose later, roughly delta to the minus 2. And all of them follow from the following distribution. So where the probability that chi I is equal to chi, this is proportional to the Fourier transform A hat chi squared normalized by the density A. Okay, so given this sample, I will now construct, say, an estimate F for this convolution A star A. We construct a function F where f of x is simply a over m times the sum of the characters I at the element x, and here maybe I have to rotate a little bit for the face. And let's note that these terms are always at most 1 in absolute value. Sorry, this is just a definition. I will.
What's this a hat squared divided by?
Oh yeah, a hat chi I squared dividing by its absolute value.
Squared,
Yeah,
then,
I will. I just for now it's the definition.
but isn't it always one?
Oh, this okay. I guess I'm not making assumptions like asymmetric. So just to be careful, that this could be a complex value.
Okay.
This is why I have it here. But anyways, it's some number in a complex plane that have modulus 1. So it's on the circle. Yeah. So of course we have defined everything in order to make sure that the expected value over the randomness of the samples chi of f x, so f is a random function, and for every x, the expected value of f of x is exactly the convolution of a at x. And as we have noted, all of the terms in this average over m random terms have absolute value at most 1. So by whatever we want to use here, so we Hofding or Bernstein, we have that for m, which is of order delta to the minus 2 up to some log factors. For every x, we will have that f is a good approximation to the convolution. Okay, so given this, what we will do is the following. So for every set A, with the conditions that we had before, so A is equal to T, A plus A is equal to K times A, and this level set L delta of A is large, we find, we put here the form star, we find a function f of the form star that approximates the convolution A star A very well everywhere. Now we will put into our cover f delta the level set x where f of x larger than 3 delta over 4. Okay, by our guarantee on the function f, how close it is to A star A, we can immediately see that this set that we put into f delta have exactly this property that we claimed here. We sandwich between L delta A and delta over 2 of A. So the last thing to see is that the total number of sets that we put into the collection f delta cannot be very large. Well, but we can count how many function f, rather how many very good discretization of this function f of the form star that we could have. So here we have m characters. So m is about delta to the minus 2. We can pay the cost to identify these characters. And then we can similarly pay a small cost to approximate very well these kind of rotating phases. And we can see that the complexity of identifying a function f of this form star is going to be at most the bound that we claimed, which is exponential in big O tilde of delta to the minus 2.
But this below, I mean, this tilde has log n in it.
This tilde has log n in it, yeah. And it's important, it must have log n in it. Yeah, so the tilde high is think exactly one log n, but then a few of the log k's. But okay, for now, that completely ignores the story for the logs. Okay, everything was good. Right, so that give us the proof of both of the cases of the cover lemma and also the answer to the question of Shahar that I told you earlier. So with the remaining time, let me, as I promised before, revisit what more precisely one can do when we restrict ourselves to a nice abelian group like Z mod n, where there's additional structure that we can use. Okay. So in this last part, we'll focus on Z mod n, and even let's think just about the case where n is prime.
So just to ask, if it was non-abelian, your only problem is that you don't have Fourier basis, you just have some representations.
So
You don't know what to do with them.
still, I think for this argument, it still works. We can still use the non-abelian Fourier transform, and we can still push this argument through. The setting that will be problematic is, well, this would not make sense if we don't know the combinatorial setup that I mentioned in the talk last year. So all of this Cayley graph setting can be pushed to this more general combinatorial generalization where we kind of have proper edge coloring on the complete graph, and we choose a random subgraph, which is a union of the color classes.
Yeah, but then you cannot use them.
There's nothing like this that we can do there. So such an improvement, we don't know how to prove in the combinatorial setting. I think that's an open question, whether one can get an improvement on the exponent of p to the minus 2. This p to the minus 2 still holds in the combinatorial setting,
Yeah.
but
This 3/2 even, you don't know how to do.
to prove for the
it.
combinatorial setting.
But in the group setting, even non-abelian.
We can still-
Similar.
Right, we can still prove it. Right. Yeah, so I say that, I guess for us to think more naturally, I stated it in the abelian setting, but the bounds and the argument does work in non-abelian groups, but not combinatorially. Okay, this last part though, there's no non-abelian group anymore. In fact, there's no general abelian group. We'll just be talking about Z mod n for prime n. So if you recall earlier, I mentioned that there's a very nice result of Green and Morris, where they show that for p, actually for any constant parameter p independent of n, the independence number of the Cayley sum graph G plus p is going to be 1 plus 0 of 1 times the corresponding analog for the Addition random graph. So we could ask how robust is this precise result where the Cayley graph, random Cayley graph behave exactly the same almost as the Addition random graph. In fact, there will be a key difference. In fact, the independence number of the Cayley graph G plus P will be strictly smaller by 1 compared to the independence number of the Addition random graph GMP, which is very interesting, but still on the asymptotic level, they behave similarly, which is not true for every abelian group. We can ask whether this type of behavior holds true still in the sparse regime, where p is allowed to go to 0 as n grows. And there's a nice recent result by Marcelo Campos. All names correct. And Dahia and Marciano. And they show that this is still true if p goes to 0 very slowly with n. So for p, at least something like log n to the minus 1 over 80, the independence number of the Cayley sum graph of Z mod n is 1 plus 0 of 1 times the independence number of the Addition analog. Okay, so again, since this is the sparse regime, what they need to achieve, as we have observed before, is to kind of build a cover that allows us to beat the naive union bound, and they build a cover that's kind of similar to the one that we have seen for the easier regime in this main cover lemma. And together with, but still, in order to get the precise result, as we will soon see, they need lots of results from additive combinatorics, including everything that we know about modeling lemma results around classic structural results in additive combinatorics, as well as a robust version of the Freiman-Ruzsa's lemma, which I will mention to you a little bit later on. And most of the content of the paper, most of the difficulty is in deriving this robust result in additive combinatorics, this robust Freiman-Ruzsa's lemma. So let me mention that Nenadov told me that he comes in and optimally pushed all of the pieces in the argument of Campos Dahiya and Marciano. And if you push over everything, then we can get that the same result would hold up to something like log n to the -1 term. Okay. And once we want to go beyond that, then we will start to run into some barrier. So I should never use that. Let me mention some of the points that one should be careful if one wants to get a sharp result in this setup. There are kind of two barriers. So the first one which would hold whenever you want to push the sparsity below log n to the -1. So in this case, if okay, maybe let me say it this way. So for the sharp result, we'll have to be very careful with the log n, all of the log n factors. Okay, so while p is going to 0 quite slowly, the independence number will be roughly about p inverse times log n in the Additive case. So that's still kind of on a small polylog level. And if we lose at any point in the argument, in the counting or in the construction of the cover, some additional log n factors, is kind of game over for getting this sharp asymptotic. And this make it very tricky because in order to push through the original argument, Campos Dahiya and Marciano, what they use is they use rectification technique and modeling lemmas. So rectification technique is a way to say that if you have a set with very small doubling in a cyclic group Z mod n, then you can model it, the Freiman sense, as a subset of the integer. So you can kind of forget about the torsion if you look at it appropriately. And we know that the rectification would fail as soon as the doubling exceeds log n. So if you want to prove anything where now the independence number can grow quite a bit faster than log n, to the 1 plus some small power, then one have to be very careful that rectification would break. And then efficient modeling we would also not have. And so all of these results will no longer be available if we want to push the density P further below log n to the -1/3.
But why do you insist on this very sharp result? I mean, it's much easier to get just off, just up to a constant. What you get in Additive is this much easier.
So in fact, for over Zn, the earlier result of green, it was easier to get up to a constant, but not
one more.
Yeah, but still, it's not completely trivial to get up to a constant over Zn, because again, it's a result where you have to specifically use the structure of Zn somewhere. It's not true for other abelian groups, right? So somewhere that has to
for
go.
telling us all the stories, it's much easier to tell us what happens if you just want a constant factor.
That is true. And maybe if you are losing a constant factor, to think a little bit how much easier that will be. But there's some aesthetics in getting this sharp asymptotic in the random Cayley graph and Additive. So in terms of a result, it's nice to know that in a large range, it behaves exactly the same as the Additive.
I agree. I'm just talking about our understanding of what you're going to tell us as opposed
I see.
The aesthetics of the final result. We will believe that we get
Yes.
the aesthetic result.
Okay, I will. Right. Okay. When we get to the later part of the story, I will try to appropriately massage it to maybe potentially just get at the weaker result, which is up to a constant here.
By the way, if you take Zn squared, it's still true?
If you take Zn squared, this should still be true. And I think that with the techniques that I will tell you, it's still true that you can use it to prove it for something like Zn squared, as long as the power that you put on top of Zn is not growing too quickly. Yeah. So, yes.
Can you say what the earlier result of green is? Is it to get like a constant times alpha
Yeah.
GNP for Z mod NZ n prime or any abelian group? And like what was the range?
No, so yeah, so the earliest result of green was to show that in these cyclic groups Zn specifically
With n
for constant p, and I think there you don't need the restriction that n is prime.
a constant.
Yeah, a constant p, n is anything. You get that the independence number is up to a constant, the addition. And the point of the Cremorris paper was to get this asymptotic for constant p. Yeah, I think for many of the things that I will mention next, it will be probably is equally hard to get the constant up to a constant or to get the sharp asymptotic. There will be some range of parameters that we can ignore when we only care about a constant and not the asymptotic. But anyway, it's the range of parameter that's less interesting, so I will not tell you about them anyway. So okay, we'll see what happens. All right. Okay, so this result in the we can significantly push over this barrier if we combine what we have over here of the cover lemma together with interesting results in additive combinatorics. And this is where it ties back to the dense regime, because now we will obtain these results in additive combinatorics by our combinatorial approach when we analyze dense random Cayley graph. So the theorem is that if P is bigger than log n to the minus 2 times some polylog factor, then it's still true that alpha g plus b is asymptotically the same as alpha of g and p. So fourth, we expect that the range where this sharp asymptotic in fact holds is much longer than this range of parameters that we have here, which is still in the polylog regime. But that I think all ties back to this delta to the minus 2. So the exponent of 2 is suboptimal in the cover lemma. We expect it to be delta to the minus 1. If we can show anything that is more like delta to the minus 1, then we can significantly extend the range of sharpness of this field.
What's the most you can conjecture? Like,
Polynomial.
So certainly polynomial, and probably can get even quite close to density that is of order 1 over n. So of course, once it's too low, then it's order 1 over n. It starts to behave differently from the Additive one. Even the random regular one behaves differently from the Additive one at that point. But if you are above that, you expect.
so like degree log n, you expect?
Well, maybe don't force me to be precise up to the log levels, but let's say the degree root n, I would confidently. Yeah. Sure. Okay, so what's more interesting is not maybe the result, but what goes on behind this result. So I'll tell you maybe the scheme for getting this type of theorem. And the key part in the scheme will be actually one step where more interesting additive combinatorics comes up, and that's kind of what I want to tell you about. So that's similar to what I mentioned earlier in the paper of Campos Dahlia and Marciano. The interesting technical contribution is actually a result in additive combinatorics, the strengthening of the classical Feynman-Ruzsa theorem. So this may be our strategy for proving the result. So let's think about our set A as having size t. T is about 1 plus some small parameter theta times log 1 minus p of n. This is the Simonyi random graph independence number. So this is our strategy. We have a few steps, so just lay out some of the steps and we'll focus on one of them. Okay, so we start with our set A, which sits inside this prime cyclic group, Z mod NZ, and it has more doubling. So in the range, let's put ourselves in the EVA range first, and I think maybe up to a constant, this is the critical range that we should think about. If you want a sharp result, you have to extend this range more significantly, but we can maybe temporarily forget about that for a second. So in the range where k is much smaller than log n, you can use rectification, rectify, to find a Feynman model A prime for A, but now A prime is sitting inside the integer with no torsion. So just to tell you briefly what I mean by a Feynman model here, this means some subset A prime of Z together with a bijection between A and A prime, so that if you have any linear relations of a short length among the elements of A, say A plus B equals to C plus D, then after you take the map into A prime, the same linear relation hold on A prime and vice versa. So that's what it means to be Feynman isomorphic. And that's what I mean here by A prime is a Feynman model of A inside the integer. So after we do that, then we can apply the modeling lemma, Ruzsa, on Green and Ruzsa. And this would now allow us to find another set. I should call it maybe a tilde. Yeah, a tilde that is a Feynman model or Feynman isomorphic to A prime. But now the set A tilde is sitting inside some much smaller group, inside Z mod M for a much smaller n. A to the big O of 1 times T. Okay, so why did I split this into two steps? The main point, which maybe I will not get to now anyway, is that once the parameter P is going to 0 as fast as something like log n to the minus 2, this T will can grow as fast as log n cubed. And the doubling K in principle can be anything as big as log n cubed. So when K is significantly bigger than log n, in that case, it will not be possible for us to find this rectification A prime of A inside the torsion-free setting. And this finding this model in the torsion-free group Z is important for us to be able to have this efficient modeling lemma. Otherwise, we'll have to get a much worse bound on M here that will be too costly for us to derive the result that we want. So kind of these two steps you have to appropriately modify once the parameter K becomes larger. And that's kind of another interesting point, but I will not go into that detail. So once you have these two modeling steps, then what we do now is we apply our main cover lemma, not inside Z mod N, but inside this much smaller group Z mod M. Okay, and in particular, what this produces is that for every, let's say, A hat inside Z mod MZ with small doubling, we can find some appropriate dyadic delta. We can find some F delta in the efficient cover that we constructed before, such that this F delta, or before we only care about the size of this guy, but now we will see that will be important that we use fully the fact that this set that we put into the cover contains fully some large level set of the convolution of A hat. Okay, so after the third step, we now have this efficient cover, but it's not the cover that we care about. We're covering this collection of sets A hat plus A hat inside Z mod M. A priori, it has nothing to do with the sets inside Z mod N that we care about. So we need to somehow find a way to map back these covers inside Z mod M to the setting of Z mod NZ that we really do care about. And in order to do that, it turns out that the key ingredient that one would need is the following result that's completely inside additive combinatorics. So let me call it a robust Feynman lemma. Okay, so say it this way. The first version that I will state it is the following. So just write it and I'll explain to you what the terms mean. So let's say that I have a set of integer a prime with robust Feynman dimension d. Okay, I need to explain to you what it means to have Feynman dimension d. We'll say that a set A prime has Feynman dimension d if there exists a subset A double prime. Okay, so here A prime has dimension d if there exists some other set inside now z to the d such that A prime has full A prime prime has full span in Rd, and A prime prime is Feynman isomorphic to the set A prime. Okay, so this is exactly what it means to have Feynman dimension d. And here we want some robustness in terms of this dimension, which just means that if we modify the set A prime a little bit, then the Feynman dimension of the set A prime doesn't significantly change. It's kind of a small technical point. Let's not dwell too much on that. But the conclusion of this assumption that we want is that the level set L delta of A prime will have to be large. We have to grow at least like d times the size of A prime. So here, we are under the assumption that the size of A prime is quite a bit bigger than the ambient dimension d that we are talking about. Okay, so this lemma actually is the main lemma in the work of Campos, Dahlia, and Marciano. And if you know what is the classical Feynman's lemma, Feynman lemma tells us that if A prime has Feynman dimension d, then the subset A prime plus A prime will have size at least d times A prime. So this is kind of a robust version of that. We don't want to just talk about elements in the subset. We want to talk about elements that are represented many times. And under this type of assumption, we can prove this strengthening of Feynman's lemma.
Does this set need to be high-dimensional?
Hmm?
So when you say that A prime is robustly
Mhm.
d-dimensional, like how quantitatively robust are you?
Yeah, so I have this little of one here, and here what I mean is that there's a parameter epsilon that you will fix related to this epsilon, and no matter how you remove an epsilon fraction of A prime, its dimension doesn't change by more than a 1 plus epsilon prime multiplicative factor in front of d. So
But do you have a quantitative relationship between these epsilon and epsilon prime?
you can get a quantitative relation. I can't maybe tell you off on the top of my head, but these are. Yeah. Yeah, it's interesting to push this epsilon to be very small for now. Yeah. I don't remember exactly what is the relation we would get. And in return, this lemma is actually proved by another one that is interesting because it follows up on a very interesting phenomenon in additive combinatorics that was discovered somewhat recently. So this lemma says that if we have A prime inside ZD, and it is full span again, then we have Feynman's lemma, which tells us that the sum set is large, roughly d times the size of A prime. But furthermore, we can prove a much stronger result, that there exists a subset A bar of A prime with very small size, with size at most below epsilon of d. So the dependence there depends on the dependence here, and the dependence here can't quite remember exactly, but it's somewhat reasonable. Such that the sum set of A prime and A bar already essentially achieve the Freiman lower bound. Okay, so that result can be quickly reduced from this, and again, this is then the main work inside the paper of Campos, Tahir, and Marciano. So maybe don't have enough time to tell you the full story, but the main point of pushing over the barrier around log n to the -1 is to be able to prove the following strengthening of these two results. So instead of, because we will fail to rectify our set, we'll have to work directly inside the cyclic group Z mod n. And here, instead of the Freiman dimension, we'll have to talk about the Zn Freiman dimension, which still makes sense, at least for any prime n. This is the same as before. We have Zn dimension d if there exists some image in Zn to the d with full span in this group Zn to the d, and that is isomorphic to our set A prime. And then over Zn, Freiman's lemma actually is a lot harder to prove. So over Zn, proving Freiman's lemma is the same as a strong resolution of Ruzsa's conjecture over specifically the prime cyclic group Zn to the d. And that was still, that was proved by Green and Tao in the case of characteristic 2, and then Evans, Zohar, and Lovett in general for every prime characteristic. But anyway, in their result, given this type of assumption, they will tell us that the sum set A prime plus A prime is large, is at least about d times the size of A prime. And now we will need to be able to push that to the robust version. Already in Z, this is challenging, so we can see that this could be a lot more challenging in this cyclic setting. So the conclusion we have is exactly the same. And now the proof for us to prove it is exactly by proving the following strengthening of the result over Z to the prime cyclic case Zn to the d. We have exactly still the same result. And this proof that we have, which anyway will give a short proof of the result over Z to the d, follows from adopting a purely combinatorial perspective. And can't tell you the long story here, but this is kind of how the lesson in the dense case allows us to get the tool that we need to analyze the sparse case. So I'll just conclude by saying that once you have step 4, when we have the robust additive combinatorial input, then we can indeed map this collection F delta inside Z mod MZ back to some other collection F bar delta inside Z mod NZ, and the size of the collection F bar delta will be at most roughly kind of the correct, we have an additional parameter D, correct power n to the d times the size of the collection F delta. Okay, maybe it's not enough time for me to tell you all of the detail, but so we don't have to worry about the detail here. And the point is that once we have this, we can map the image in Zn back to Zn, and that will now allow us to conclude the proof. Okay, we'll use this cover to rule out the existence of large independent sets in Zn. Okay, I think I'll stop here. Question?
So you have two fairly kind of different ways of upper bounding F delta there.
Yes.
So I mean, currently you're just kind of saying, okay, you take the minimum, which one does better.
Right.
Like, but is there some way in which you could kind of combine the two arguments and get at least in some regime?
Good question. I have tried to do that for a while. I don't have a good answer to that right now. Yeah, you could imagine that somehow the right thing to do is you have a physical space argument, a Fourier space argument. You want to ideally combine it in some interesting way. It's not clear how to do that at the moment.
Other approach you outlined roughly follows union bound or first moment method.
Yeah.
So is there intuition why that's enough, that you don't need to consider higher moments?
Yeah, that was last week.
Oh, sorry, okay.
Sorry, yeah, so last week we mentioned
Okay,
how there must always be a correct version of the first moment that tells you what you expect to be true. So yeah, the sufficient.
Luckily, it was recorded. Yeah, it's a nice
Right.
connection. to
But
this.
yeah, but it is exactly the point that we, well, last week we were kind of always in this very abstract setting, and we discussed a very kind of powerful abstract results, but it doesn't mean, even though how powerful these abstract results are, it doesn't mean that we necessarily know what to do when we are facing any specific problem. So this week is kind of a specific instance, a specific problem where even if we know in advance the abstract framework, that can only give us some confidence, but that doesn't tell us how to execute the argument correctly, how to find these colors.
Also, so I mean, you were focusing in the sparse regime on random generators, right?
Right.
So is there something interesting that happens if kind of you get adversarial generators or
Yeah.
sparse worlds?
So there are lots of questions around Cayley graphs with adversarial generators, and usually they stay in the extremely sparse regime. Right? That's when it becomes more interesting. Right.
So we see much larger independence sets if you're not adversely pieced.
Yeah, well, if you think about properties like the independence number, then it's not very interesting if you allow someone to pick the adversarial generator. But if you want other type of properties, you know, connectedness and these other type of properties, then you get interesting, challenging questions.
I guess I didn't really mean adversarial. I meant just if you get an arbitrary generator set, can you say roughly what's going on with the alpha? So I mean, adversarial means you can get a much different behavior than in the random.
Yeah, but I guess if you are staying in some group, like in the abelian group like Z mod n, then the behavior can be kind of maybe as trivial as it can get when you are handed an arbitrary set of generators in terms of the independence number. Still, of course, if you focus on an interesting group, I don't know, like a very interesting non-abelian group like the symmetric group, then you could have maybe interesting questions there. Yeah, but if you're in the abelian world, then you want something random for it more interesting.
So the Fourier something you used gave you the delta power -2.
Yeah.
Because you want to get every element approximated correctly.
Right.
If you don't, I mean, if you
don't,
most of them, or you get.
Well, if you want all of them, here you pay the log factor, which is, as we see in the end, is not so important to us. If you want most of them with the random sampling argument, you still need delta to the -2. I have a completely different proof. If you want most of them, I have a completely different proof to get delta to the -1.
Without the log. Delta to the -1.
Yeah.
Most of them.
For most of them, I can get an argument, but to get even delta to -1, a sharp exponent, but it's not through the same argument that we saw, not through Fourier sampling. And then again, my story is I don't know how to combine these two different regimes together. It's very important for us here that we are not just approximating the sum set A plus A. We have to approximate it from the inside. If we get any element that may lie outside, even though there's a very small set of such elements, it doesn't allow us to go on with the proof. So that's kind of one of the difficulty. And yeah, let me mention that, so one question that, as Ami mentioned earlier, is we don't know at all how to execute this proof in more general combinatorial context. And another question that is interesting, suddenly I forget what I just thought of, is, okay, maybe, yeah, sorry, when I mentioned the first question, I forgot the second one, so. Yeah, so I think anyway, it's interesting to see what can we remove the use of Fourier analysis here? Is it really essential? Do we really need the group in this result? Or we can do it combinatorially without a group? I think that's an interesting question.
Okay. More questions? Thanks so much for the 2 questions.